Hello and welcome. So this video is going to cover the lesson and exercise called range and endurance. So flight for maximum range and endurance. In Canada, this lesson is delivered prior to slow flight, and you'll see why, because we set it up as a continuation of the power curve instead of only being needed for cross-country flying. Now, you can use this information however you choose, and this is just an example of the types of PGIs that I deliver. So a PGI is a preparatory ground instruction. This is the mini lesson that happens prior to getting into the airplane. This is not ground school. So this is a mini lesson only to help the student then accomplish what they need to accomplish in the airplane. So enjoy. Oh, as a side note, I'm recording this in one take. So if I flub my words or if I make a mistake, you can pretend it's an in-person conversation. All right, let me share my screen and we shall get going. Okay, here we are. Once again, this is exercise 10. So this is immediately prior to slow flight. And the students should have mastered, not just seen or practiced, climbing, descending, turns, various power changes in straight and level flight, and trimming. So the student needs to have mastered those items prior to starting range and endurance. And if they have, and they can answer all questions properly, and you've marked it down in the student file that they are doing a really good job, and they can perform those functions without instructor help, including knowing where to look and proper yaw control. All right, so then you're welcome to the course. Here we are. All right, so by the end of this lesson, you will be able to handle the aircraft in situations that require flight for maximum range and max endurance. And you will also be able to apply the lessons learned about range and endurance using the POH for estimation. Why do we do this? What's the point? Well, being fuel efficient in normal and emergency situations is key to good airmanship and safety. If I were to break this down into simple terms, it's a trimming exercise. So it's helping the student, prior to any of the difficult exercises, it's helping the student understand the lift trade-off and how they can handle the airplane, what angle of attack really means, and of course, last but definitely not least, is trim. Can they fly the aircraft using attitude only and then trim the aircraft to be hands-free and show the instructor and show themselves that they have solid control over the aircraft, okay? This lesson is the beginning of a series of very complex aerodynamic situations that's coming up. So in plain terms, it's key to understanding what's about to happen. Now, I usually start with a threshold knowledge test with my students prior to even announcing this information, but here we are. So we can start with a threshold knowledge test here. Ask your students, how do you speed up? How do you slow down? And how I do that with my students is you give them the tiny model aircraft and you say, okay, so just to review straight and level flying, because trimming and power changes in this lesson is key. So I'm going to ask the student, how do you speed up? In which case they'll say add throttle, and then hopefully they'll mention that the nose pitches up, but attitude plus power equals performance, as we mentioned in the straight and level lesson, plus the lift trade-off. They would have to go from a normal cruise attitude to a slightly slightly lower cruise attitude with the additional power, because the power equals air over the wings, which means more lift. And if to stay straight and level without climbing, they would have to then decrease the angle of attack to decrease lift from angle of attack. So it's the lift trade-off to make sure the straight and level can happen. Then I'm going to say, how does the airplane slow down? And then what they're going to tell me is they're going to remove power, raise the nose, and trim for the new nose higher attitude in normal cruise attitude. So hopefully that comes along. Now, if we're going to go ahead and get into this, okay. So then what is angle of attack? You show them the airplane, or you give them something to draw, or you give them a page. Do not answer these questions for your student. If you say, what is angle of attack? They should be able to say, it's the angle made between the chord line, which is a line drawn from the leading edge of the wing to the trailing edge of the wing. Yes, flaps are included in that, but the leading edge to the trailing edge. So that's a line from front to back. and the angle of the relative airflow. Now, when I describe or when I initially teach angle of attack using a model aircraft and not just drawn, well, actually, even when I do draw it, I'll always start with a wing, even in the drawing, a wing at a normal cruise attitude. Because what happens if you start with a drawing with a nose up attitude, or even drawing the wing in a nose high attitude, the student with the learning law of primacy, they're going to see that, capture it as the first experience of angle of attack, and think to themselves always that angle of attack, a high angle of attack, is a nose high attitude. We know that's not true. If we have wind coming from my silver pen and the aircraft, or relative airflow, and the aircraft is descending, relative airflow hits the wing at this angle. It's a high angle of attack, but it's not a high nose attitude. So in the very first iteration, the very first time you draw this for your student, make sure that you draw it or even show them at a normal cruise attitude and relative airflow coming from here, or relative airflow coming from here. Don't start with this, because that'll cement in their brain that they always think that a high angle of attack is a high nose attitude, and that's not true. Okay, so for angle of attack, they must be able to describe chord line, be able to describe relative airflow, and describe the angle between them. That is their job, not your job. Anything on the threshold knowledge test, they must complete without you. If they cannot complete it without you, they cannot move on to new material, because you'll be overwhelming them with new stuff they haven't mastered, and then suddenly it piles on them. It'll force a plateau later. They will think they're stupid. It's actually your fault. Sorry to be so blunt. Okay, so the next question I had on there is, what is the mixture? This is pretty obvious. It's very important for fuel efficiency. So they should be able to point to the mixture control knob on the poster panel that you have in front of them and describe how to lean it and what exactly it does. And then last question that you're going to ask them on the threshold knowledge test is, what is trim? So they'll describe the, my airplane is very, very old. It's missing some parts, but it's hilarious. So they'll describe that the trim tab is on the back of one elevator, unless you're using stabilator, in which case it spans the entire thing. But the trim tab is here. They should be able to describe how the air flows over the elevator, and then how the trim tab keeps the elevator down, because this information was presented during the straight and level exercise. All right, moving on. Now, okay, so after we get through the threshold knowledge test and the student is accurately able to explain all of that information, then we get into the outline. A written outline is incredibly important. You can have this on a handout, you can have it on written down on the board, you can have it written on the slide, as long as you give your student time to write it down, because the outline, visual outline through the entirety of the presentation, allows the student to, if you will, check boxes. It allows the student's mind to follow the progress of the lesson, and the lesson plan structure, including an outline, should be the same every time. So not to overwhelm the student by jumping around. Lesson plan structure, one item within that lesson plan should be the outline, and it must be visual. It has to be either on the board at all times or in a handout, or you must give your student time to write it down so that they can have that visual checklist as they go through this lesson. So what we will be covering is, of course, the definition of range, how to find the range profiles in the POH, and then, of course, factors that would affect range. We're then going to define endurance, and then factors, or how to find the endurance profiles in the POH, and then factors that would change endurance. Then we're going to get into the experimental method of the emergency situation. The experimental method, as you'll see after we go over the POH items, is the emergency situation that you can experiment with. So you can find the absolute maximum range, the power setting and airspeeds to go the absolute exact farthest distance possible. And then, of course, also in endurance, the power setting and airspeeds to find the exact longest amount of time that you can stay in the air. Okay, and then, of course, last but not least, always, we have safety to talk about in every lesson. So to start off with range, like it says in our outline, we have the definition. This is the furthest distance traveled per unit of fuel. In Canada, we have the flight training manual, as you see in the video here. We have the flight training manual. All of this information is found in the flight training manual. I believe in the FAA following countries, I believe it's the Airman's Flight Manual, or I forget what it is. I shouldn't even go in there, but there we are. Okay, so back to the lesson. Let's say that you're in your car and you have half a tank of gas, and the next fuel station is 250 kilometers away. Could you make it? Hmm. If there was no other option, how would you drive that car as to stretch the fuel as far as possible? There's a strong chance that your younger students won't be able to answer this question because they don't know how to stretch fuel. They don't know that going slower will burn less gas than going faster. But of course, in a car, there's always that sweet spot, like how slow is too slow so that you're wasting time, how fast is too fast so that you're wasting gas. You don't know. So another way to say this would be, let's say you have half a tank of gas and the next fuel station is 250 kilometers away. Can you make it? The automatic answer from your student should be, I don't know. How big is the gas tank? And that is an exact perfect segue to get into if we carry more fuel, we can go farther, right? It seems like a simple connection to make, but it is your job as an instructor to say it out loud. Now, another connection to make would be, let's pretend that we have a full tank of gas, and that will allow us to travel, I don't know, 600 kilometers. Let's go 700 kilometers. And that 700 kilometers travel will take us 6 hours to travel there. Okay. So let's say we also have a full tank of gas and we're sitting in a parking lot going nowhere. The car is idling, or even in the driveway, it's going nowhere and it's idling. Do you think that car can idle for longer than 6 hours? Right? So if we're driving at highway speeds, it'll take us 6 hours to run out of gas. But if we're idling in the parking lot, how long can we idle? Will it be able to idle longer than 6 hours? So this is a perfect connection and segue into the difference between range and endurance that we will need to spell out for the student later on as we get into the theory. All right, and so this is exactly what we're going to be discussing in this lesson. We talk about the owner's manual that your car has versus the POH, which is the owner's manual for your airplane, and then of course how to handle the machine after that. Now, here is your owner's manual, the pilot's operating handbook. I highly suggest you get your student to, as you're going through this lesson, you get your student to pull out the book exactly right now. This serves two functions. Number one, it's student engagement, and it gets them involved in their own learning instead of sitting passively. But number two, you're also empowering your student to see where this information is, where they don't need you. If you tell a student, say, for example, you tell the student that in a 172 certain model, certain year, this is a different lesson, not this one, the VX or best angle of climb is 59 and VY is 70. Then if they forget, they have to come back to you. And if they forget, they have to come back to you. And if they forget, they have to come back to you. The purpose of opening the POH right now and showing the table of contents is so that they can see where you got this information. It's not your opinion. It's not some mystery, some magical section of being able to magically come up with these numbers. You are empowering your student to find these numbers themselves, and it'll be in the same section of the POH each and every time. So for range and endurance, we're going to crack it open. We're going to go to the table of contents to right here. So the performance section, we're going to go to the performance section. So when they open section 5, the performance section, then we're going to hunt down the range profile charts. When teaching a chart, you must always read the chart title. I know it seems silly, but you are setting up your student for habits. Guaranteed, if they've been driving a car before this, they have never opened the owner's manual, unless you have that one mechanical student that's probably 50 or been working with his or her dad on the car for a long time. Guaranteed they've never cracked open their owner's manual. So you have to show them how to use this book. Therefore, open to the page, you read off, okay, so this is the range profile chart for the aircraft with 45 minutes reserve. Now, this is in Canada. You know, there's certain rules in Canada for why 45 minutes, but the 45 minutes is just what the manufacturer has chosen. The FAA or TC or CAS or whatever your governing body is will have their own specific requirements for day or night or IFR, whatever it is. And you'll see up at the top, it says on the left-hand side, it says 40-gallon usable fuel, and on the right-hand side, it says 50 gallons usable fuel. You have to point this out to show the student that there are two different graphs, two different charts in this book, and they have to choose the right one. How do you find how much fuel your aircraft has? And then that starts a discussion. Then you must go into the condition section. Before talking about the chart, before labeling anything, you must talk about notes and conditions. Read them out. and have them maybe come up for themselves that 2,300 pounds is gross weight and zero wind, standard temperature. These are perfect conditions. The chances of them ever being able to fly in perfect conditions are almost slim to none. Therefore, already in the conditions, we're kind of setting ourselves up to not have accurate graphs here. Plus, yes, it's an old machine with an old engine, and so the graphs aren't going to be perfectly accurate. In the notes, you can read those off. And then a question that should come up in your student, whether they say it out loud or not right away, the question that should come up is, what does 45% BHP mean? You know, I've flown this airplane 4 times and there's never been a percent BHP instrument in the aircraft. Therefore, we get to talk about what exactly that means on the next page. So I will tell you what percent BHP means. We're going to discuss what this means, but hang on, we're going to talk about the rest of the graph first, okay? So then you label the graph. You go through altitude versus nautical miles, and you give them an example. Let's say let's blow it up to make it easier. Let's say we choose 6,000 feet and we're heading over to the line at 45% power. And then at 45% power, it looks like we're going to be just less than 575 nautical miles. So if we're just less than 575 nautical miles, then we do have to think about those notes and conditions now. And also the fact that this is a guideline, right? So if we have wind, it's going to be different. Obviously, if we have a headwind, we're not going to go as far. If the airplane is lighter, then we don't have to produce so much lift. And that lift trade-off that we spoke of before, we can either decrease the angle of attack, or really we're going to decrease thrust so that we can save fuel. We might be able to go a little farther. If it's not standard temperature and we have super cold weather, we'll be able to go farther. If we have super hot weather, we won't be able to go as far. So stopping right here with your student and explaining that these notes and graphs are a guideline and should not be taken as rule is very important. How do we know exactly how far the airplane can go? How do we maximize our fuel to go as far as possible? Well, we're going to get into that in the experimental method, okay? So now the cruise performance charts, you're going to flip the page backwards one, and you're still in section 5, as you can see at the top of the page. We read through the conditions. We have gross weight, recommended lean mixture. They should know what that means by now, but then you get to tell them how to read the graph. Here is the percent brake horsepower column. There we go. That's the word I'm looking for, column. And then you can go through an experiment with them. So if we're at the 4,000 foot level, you can see all the RPM settings and how those RPM settings relate to the percent brake horsepower. So 2,100 RPM equals 46% power. That's just like what was on this graph, wasn't it? Look at that, 45% power, 55% power, 65% power, 75% power. So if we go into this, you'll see that we have very, very close to 45% power, which is 2,100 RPM. And then 2,200 RPM equals 51% power, and they should be able to make the connection right away. Also, if that 46% brake horsepower equals 2,100 RPM, it also equals 93 knots, knots true airspeed, and it also equals 55 gallons per hour. So this chart will show them that if you increase the RPM setting, increase the percent brake horsepower, they're also going to burn a heck of a lot more fuel. So this is where you can maybe have them analyze the numbers between how much fuel you're burning to how much airspeed you get. But honestly, that analysis should be left to ground school because this is a tiny lesson before you get in the airplane. All they need to understand is that more power equals more fuel burn. That's pretty much what they need to understand right now. Okay. So factors affecting range. This one, you instructors, you have to go through one by one. If we increase angle of attack, you can see me on the tiny little video right there, we increase angle of attack. What is also increasing? They should say induced drag. If induced drag increases, what does that do to our airspeed? It's going to lower it. Okay, so if increasing angle of attack lowers the airspeed, then we might not be going as far. Correct? Okay. So of course that leads into the next one. If we have an extremely high airspeed, it also might mean an extremely high power setting, which means we're just piling through the gas. Could mean that we're in a descent, which means we're definitely not going to go as far. Okay. So talking about how the factors would affect those charts that we just looked at is important. Wait, if you look at the little video here, if we have more weight, we also need more lift to counteract it. So if we have more weight, we need more lift. What are the 2 ways that the pilot has control over lift? Well, we can add angle of attack, which would slow us down, add drag, and we can add thrust, which would burn through fuel faster. So this is important. Center of gravity. So this string on my little airplane is my center of gravity teacher, or actually my yaw teacher is what it is. So if we have a center of gravity that's very, very forward, the airplane is normally going or naturally going to be nose down, and you'll have to add angle of attack or add back pressure to keep it straight and level. If we add back pressure, which is increasing the angle of attack to keep it straight and level, we're then adding drag. If we have a rear center of gravity and we're normally in the air tail low, then we have to push forward. We have to decrease that angle of attack to keep the aircraft straight and level. We're also doing a lot of stuff to the stall speed, but don't mention any of that. I'm just saying that for your benefit. So if we have a rear center of gravity, we're going to be using a heck of a lot more nose down attitude to keep it straight and level, which would decrease the angle of attack and decrease induced drag. Okay, then we have altitude. Less air up here, like less dense air up here, more dense air down here. If we're in the less dense air, that means less air over the wings, less air into the engine, and less air being flung by the prop. That says less performance. So we're not going to go as far. But of course, if we're too low down, then we're going to be climbing, descending all over those hills. So it's a trade-off. Wind, if there's a headwind, obviously we're not going to go as far. And of course, if we have half tanks versus full tanks, we're not going to go as far. So going through these factors, it doesn't require numbers. It requires a visual representation of whether we're going to go farther or not as far, because your goal here on talking about the factors is simply to have the student understand that the POH graphs that we have are affected by 7 different things. So are they going to be perfectly accurate? No. Can you use those graphs in an emergency situation? No. So then we're just going to leave them, let them ponder that for a little bit. And then we're going to go on to the definition, POH, and factors affecting endurance before we get into the emergency situation. So here we are. All best range and endurance practices depend on a properly lean mixture. I've said that before. It's in the middle. It's going to be at the end as well. Okay. Then we have the definition of max endurance, the longest time spent in the air per unit of fuel. The immediate question that's going to come up in your student's mind is, how is that different? Do you think if we can go as long as possible, that would be able to spend obviously more time in the air? But this is coming back to your first representation of the car driving at highway speeds versus the car idling in the parking lot. Okay, so endurance is about time. And now, hopefully, you're asking yourself, how is this different from range? The first question, all right, sorry, I'm reading my notes, and obviously I went through that without reading my notes. Okay, a better question would be, how is it possible to stay in the air for a longer amount of time than that of flying for best range? What would have to happen to this aircraft to be able to stay in the air for a longer period of time than best range? And your answer is not in the POH. Your answer is everything to do with angle of attack, but we're going to get there. Stand by one. So here we have the same graphs. Here you're going to point out the difference between the 50-gallon usable and the 40-gallon usable. And because you took painstaking amount of time to detail how to read a range graph, it's perfectly reasonable for you to get the student to read the endurance graph. Okay, so let's pretend we're at 6,000 feet. Let's pretend that we're using 45% power. How long can we stay in the air? The answer should be 6.5 hours, but there's a whole bunch of factors affecting us being able to stay in the air. Let's start with weight. If we have more weight, then we need more lift. Therefore, we need more power, more angle of attack. If we have the center of gravity changes, same thing. Altitude, same thing. Amount of fuel in the tank, same thing. I skipped wind. So here, does wind affect endurance? We're in the parking lot. So come up with a situation why we would need to stay in the parking lot, which means we're just burning circles near an airport waiting to land. Okay, we don't want to go far. We want to stay exactly here. We want to stay exactly in the parking lot. So does wind affect us? Well, if it blows us too far away from the airport, yeah, it would affect us. But typically there's no headwind because we're not really trying to get anywhere. We're trying to wait. Now, my fun little example is when I was, feel free to use this if you don't have your own. If you have your own, great. But when I was a junior instructor, we took some of the flight school aircraft down to the local pancake breakfast fly-in just for advertising. So we would sell $20 per seat for a 15-minute fun flight during the fly-in. In this fly-in, the organizers had arranged for a Griffin helicopter to come and do the demonstration over the runway, but they were on the ground and nobody really knew when they were going to do their demonstration. So we sold $20 a seat in my little 172. And I would take people up, I would circle the islands that we were living on at the time, and then I would come back down 15, 20-minute flight max. So on this last flight that I was about to do, I had 45 minutes in the tanks. So that means a 15-minute flight plus half an hour reserve, which is Canadian regulations on a VFR flight, so that's fine. And I launched. Well, I launched to take my 3 people around the islands, and just as I launched, the Griffin helicopter had been called out to duty within an hour. So they wanted to launch immediately and do their half an hour demonstration before they left to go on duty so that they didn't waste. Everyone was excited about this. They wanted to do it right then. So I took off from the airport to do my 15-minute flight, and the Griffin helicopter took off to do their demonstration over the runway. Well, this is bad. They have a half an hour demonstration to do, and I have 45 minutes in the tanks on a 15-minute flight of what it should have been. Bad, bad, bad news. Usually when I talk to my students, and I say this one, I get really dramatic. I use lots of emotions, lots of descriptors. I was panicked. Oh my goodness, what do? I don't want to be that person that calls a fuel emergency 5 minutes from the airport. I don't want to make the Griffin helicopter land and have everyone stare at me coming in. It's just more than I can possibly handle. So what I did is I did an experiment to find the minimum amount of fuel that I could use to stay in the air, to stretch that fuel as long as possible. If cruise power settings say that I have a 15 minutes or 45 minutes in the tanks, then what if we do much, much less than cruise power settings? So here's what happens in our lift trade-off. I will be getting to the slides in this. So the pictures that I have in the slides will reiterate exactly what I'm about to tell you. So essentially, you've covered with your student on more than one occasion, there's 2 ways that the pilot has control over lift. We can either increase angle of attack, or we can add power, which would increase air over the wings. Now, the lift trade-off says that if we increase angle of attack, we're increasing induced drag, we're slowing down. I'm not going to be able to go as far, there's more drag. And realistically, I don't care about going far, so that's okay. So if I'm going to use angle of attack to increase my lift, that's okay. What that allows me to do is then reduce the thrust. It allows me to pull the power back and just sip fuel to find that minimum power setting to keep me in the air. So if I reduce power down to the absolute minimum to keep me in the air, to prevent descent, I can trade it off, reduce lift by air over the wings, but I can trade it off by increasing angle of attack. That does increase drag, but do I care about drag? No, slow me down. If I could, I would helicopter there and just wait, but I can't. So we're just gonna plow through the air, super slow, minimum amount of power setting possible, and just sip that fuel. That's the lift trade-off. Trading to stay straight and level, we're gonna trade thrust for angle of attack. Now, okay, so wind doesn't really matter, and there's my story. And the story here is important to allow your student to see that this can be used in real life. Now, lift creates drag, everything that I just described. This should have been a lesson before they ever got to the airplane the first time about how the pilot has control over lift in the air. But what you're essentially doing is you're showing them again and again and again with repetition that the pilot has 2 ways to control lift: to overcome weight, to not descend. We can increase angle of attack, which increases drag, and we can also increase thrust, which burns more fuel. So if we're trying to find the maximum endurance to just idle in that parking lot, we're going to pull that power back as much as possible. Okay. So now here we get into the theory. This is an essential component of all of your on the ground lessons, but it is important to know that all of this theory of lift and theory of flight items that I'm going through can be a 2-year university degree. We're simply going to boil it down to a 5-minute cartoon or a 5-minute showing an airplane on the video so that they can understand it. You don't have to go crazy in depth on this one. And here we have, let's see, yeah, okay. So I'm just gonna go back to this one. The first one that we're gonna do, I know that I have an annotation possible. Here we go, annotation option. So when you're teaching your student the very first time, instead of pointing their eyes to these two graphs in the book, it is so important for instructors to draw this out and go as slowly as possible, because you are guiding your students' thought process on this one. You need to draw, oh, I need a better color. Draw, annotate. Let's go bigger one on that one. Yeah. Okay. Okay, so let's see if we can do this one. So you're drawing the graph and you're labeling the graph. Okay, so if this is drag on the y-axis heading up here, and this is velocity on the x-axis heading down here, yes, I am fully aware that they can look at these graphs at the same time. That is okay, because they will follow your marker. If it's on a whiteboard, if it's on an online Jamboard that you can both see, if it's like this on Zoom where you're drawing on the screen, you're drawing on paper and you're videoing your paper, it doesn't matter. The students' eyes will follow your pen. So we label the dimensions of the graph like we did with POH. Where is my, I lost my, oh, there it is. Okay. All right, so let's talk about drag. You ask your student the question, what are the two main types of drag? They're going to say parasite and they're going to say induced. You're going to go, great. If we're still, if we are completely still on the ground, is there any parasite drag? They're going to say no, and they're going to you say great. They say, as we go faster and faster and faster, how much parasite drag weight do we have? And they're going to say, well, we're going to get more and more and more. And you're going to say, yay, and you're going to high five. So as we go more and more and more, the increase, the faster we go, the more parasite drag that we have. And this one is labeled parasite drag. And you're like, high five, great. So now let's talk about induced drag. If we are at a standstill, is there any induced drag? And the student's going to say no. So really, if this is the 0 on the velocity chart, and this is 100 on the velocity chart, I'm making up numbers here, then really there's never going to be induced drag if we're at a standstill. Never going to happen. Induced drag happens when we're at an airspeed fast enough to actually fly, okay? So then we're going to start right roughly here. You're going to walk your student through the process of getting faster and faster and faster, which means, pay attention, which means that attitude decreases to go faster and faster. If the attitude decreases, the wingtip vortices decrease, and therefore induced drag decreases, and induced drag looks like this. Some students will need numbers. I implore you to try not put numbers on these charts, because these charts are accurate for every airplane and not just the 172. Therefore, putting numbers on it would inaccurately lead their brain to think that those numbers are law. But if the student really can't understand that we have now a total drag curve, let's see if I can get purple. We now have a total drag curve, and that it looks like this. If they can't understand it, then sometimes I'll go, okay, let's pretend this is drag number 5. Drag 0 is down here. Drag 1, 2 drags, 3 drags, 4 drags. Okay, so if they can't handle it and you need to put levels on here, then you say, okay, great, not a problem. At this specific velocity, whatever speed that is, we have 1 drag for parasite, and we have 3 drags for induced, and the equal, you add that together, and that equals the 4 drags, or sorry, 4 drags total, and you can walk them through that process. I would really prefer if you didn't put any numbers on there at all, but if they need it, then they need it. As long as what you're trying to get to is that they are eventually walking around to the point that this right here, where the 2 drags cross, is your minimum drag curve. So that is right here, okay, right there, minimum drag or lift to drag max. What this is saying, if I'm going to recap, and I hope you recap it the exact same way, is that there is a very specific speed, and a very specific speed where you can have the minimum amount of drag possible. It's not slow, it's not super slow, it's not super fast. There is a very specific place you can find the minimum amount of drag, and it's related to a speed. How do we find that speed? Is it in the book? Nope. And because it changes with air density, well, that changes hour by hour. It can change with altitude. Well, that'll change depending on where you are in your flight, right? It'll change with, like, all of the range items can change with the factors that we've already discussed. So this will change hour by hour. Is there a way we can experiment and find this out? Yes, there is a way that we can experiment and find this out, and that is what we're getting to, okay? So here, after we talk about minimum drag or lift to drag max, then we can get into the power curve, which is talking about max endurance. So once again, because you're a good instructor, the very first time they see this, you're going to draw out the graph in painstaking detail. So here's my y-axis, my x-axis. We have velocity, which is your speed. And this time we have thrust, which is power. So if this is 0 and this is a lot, then this is going to be adding power and this is going to be going faster and faster. That means that there's going to be a minimum power setting, like power setting and airspeed. There is a minimum power setting and airspeed to stay in the air. We will get to that. But essentially, from this minimum power setting, to be able to go faster, you need to be able to add more and more and more power. So we need more power to go faster, need more power to go faster, need more power to go faster. Therefore, oh, come on, where's my mousey mouse? Okay, so therefore, this is power required. We need more power to go faster and faster and faster. However, at some point, we will have that throttle hit the panel. Therefore, there is going to be only so much power we have available to us. So this is power available. Please notice how slowly I'm going through this process. This is not for you, the instructor. This is so you can emulate this for a private pilot student. At this point where it crosses, we need more power to go faster and we don't have it. This is like full throttle, straight and level flight. That's what this is, okay? Now, coming back to this minimum point, it's a specific power setting, it's a specific airspeed to stay in the air. If we use less power, we can't stay in the air. Alrighty, we use less power. So what that's saying is that if this is, I don't know, I don't want to write numbers on the chart for the exact reason I told you, but if I say, you know, this is 2300 RPM and 2200 RPM, there's going to be a certain point where you bring back the power so much that you actually can't stay in the air. The lift trade-off. Look at the little video, please. If we bring power back to be able to stay in the air, we have to trade it off by adding angle of attack. We bring power back, add angle of attack, bring power back, add angle of attack. At some point, you can't stay in the air and you get the uncommanded descent, also known as the stall, but please don't use that word in this lesson because if you say stall, you have to explain stall. All right, now, let's clear these items. There we go. Clear all drawings. So that means that when we get into the power charts, you've drawn it out, you've taken their eyes along with you, and therefore you can now show them this giant cluster of a graph and say, okay, so here's the minimum power required. This is the absolute minimum to keep in the air. Please notice how it's different than the speed that's lift to drag max. So right here, we have, this is the speed for best, speed and power setting for best range. This is a speed and power setting for maximum endurance. There's still no numbers on this graph. How do I do this? Well, so we're going to experiment with it. We're going to experiment with it, and we're going to talk about that right now. The experimental method. You have these graphs in your flight training manual for range endurance, but essentially what's happening is that they're almost useless. They're almost useless. So typically I would open another Jamboard, which means open a whiteboard, but since I can annotate on the screen for this recording, we're just going to keep going like this. So the experimental method in the aircraft is going to be 2 experiments, 2 different analysis of finding best range, finding best endurance in one maneuver, in one experiment. And here are the procedures that you're going to go through. Experimenting the aircraft. Okay, experimenting the aircraft. We're going to start at a high cruise power setting with a lean mixture. I'm going to suggest you start at 2,500 RPM, 2,400 RPM, whatever it is. And then you, the instructor, are going to set up this experiment. You're going to set up in high cruise and trim it out perfectly. It has to be trimmed so beautifully that you could let go and that nose isn't going to change a smidge from where it is on the horizon. Hopefully you've chosen a day with very little turbulence, very calm air, very clear horizon, okay? Because thinking about this is probably the student's 3rd hour in the airplane. I know for the countries that teach range and endurance, during navigation, it would be to your benefit if you were to cover this exact entire lesson right now, because it will set them up for success during slow flight. So start at a high cruise power setting. Let's pretend you start, say somewhere around 2,500 RPM. Okay. This is terrible. And then you're going to trim it out, and your student is going to have a piece of paper to write down this analysis. Now, as you go through the PGI, do this in pretend right now. Talk about the procedures and then pretend to go through this on the ground. So we're going to start at a high power setting, trim it out. We're going to note the airspeed. And then we're going to bring the power back by 100 RPM. You're going to wait for the airplane to slow down. You're going to slowly pitch up to make sure you don't descend. We're going to do the lift trade-off, right? And then you're going to trim it out to be hands-free. It's a slow, methodical exercise to help the student practice understanding what's happening with the airplane when you slow down, but also it's a trimming exercise, right? So you're going to reduce that power by 100 RPM, and then you're going to wait, and you're going to trim, and you're going to note your airspeed. And then you're going to reduce by 100 RPM, and you're going to wait, and you're going to trim, you're going to note your airspeed, and you're going to bring that RPM back as we head back down this power required graph. So we're going to get slower and 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 slower until, you know, we note our airspeed and our power setting, whatever that is. When you pull the power back by 100 more RPM, you actually can't stay in the air. You will start a descent no matter how much angle of attack you add. Look at the video. No matter how much angle of attack you add, it is an uncommanded descent because you've now removed so much lift that you cannot overcome weight. So that is the procedures. As we go through those procedures, then clear all drawings. Okay. And then here's what the analysis is going to look like. I highly suggest you do a pretend analysis in the classroom with your student right now. So you write it on the board, or you have a graph similar to this one. You say, okay, let's start at 2,400 RPM. Let's pretend it's trimmed out perfectly and the airspeed is 109. Then I'm going to pull back to 2,300 RPM. We're going to wait for the airplane to slow down. We're going to nose up. We're going to trim it out perfectly. And once we can confirm that we are not climbing or descending and we are trimmed out perfectly and everything's stable, we'll read the airspeed. The airspeed says then 105. Then we're going to bring back the RPM another 100. We're going to slow it down. We're going to trim it out. We're going to wait and wait and wait so that there's no porpoising whatsoever, and we're going to read the airspeed, and we're going to keep going through this. 2,100, read the airspeed. 2,000, read the airspeed. 1,900, read the airspeed. 1,800, read the airspeed. 1,700, read the airspeed. 1,600, wait a minute. We can't stay in the air any longer. It doesn't give us an airspeed. No matter what, we can't stay straight and level. We keep descending. We can't stay in the air. So therefore, automatically, that means that if we find that minimum power setting to keep us in the air, boom, that is the minimum power required, okay? So that minimum power required would be 1,700 RPM. We've done one set of exercises and already found the power setting for max endurance. This is an emergency situation, max endurance. Because of the factors that we talked about already, this will change all the time. Today it's 1,700, tomorrow it's 1,900. You get into a different airplane, it's a different 1,900, okay? So we found max endurance. Now, we can use the same amount of information that we just wrote down, because right now we're pretending in the classroom. We can use this information to analyze and find out where our minimum drag is. So we're going to check out the deltas. The difference, actually, I should preface this by saying that in this one experiment, we started with 2,400 RPM and we worked our way down to a power setting that doesn't keep us straight and level in the air. Those numbers should be the exact same going up as well. If we started this process at 1,700 and increased by 100 RPM at a time, it should give us the same airspeed. So if we analyze these in this direction now, we're adding power, going faster. So if we add power from 1,700 to 1,800, we've gained 5 knots. Great. If we add power and we go from 18 to 19, we've gained 11 knots. Great. If we add power and we go from 19 to 2,000, we've gained 4 knots. Great. So you're going to analyze the delta, or the change between here, and then you're going to look at those numbers. And keep in mind, please, that I made up these numbers on purpose to show something very dramatic. And what I made up is numbers that gave us an 11 knot increase. So if we went from 17 to 1800, that's a 100 RPM change, but we gained 5 knots. We go from 1800 to 1900, we gained 11 knots. Wow. We've overcome some sort of invisible drag barrier. We've overcome some sort of like crazy gate, and we gained a whole bunch of airspeed for only 100. And in fact, we don't find that kind of big gain anywhere else. Therefore, what we've done is established at 1900 today, this hour, this moment, 1900 RPM and 86 knots is our lowest point on the drag curves. So this is our lift to drag max. This is the lowest amount of drag because we've gained so much airspeed with only 100 extra RPM that we didn't have prior, right? So in that, and we didn't find that delta anywhere else. This is the biggest jump. And that biggest jump means we gained a whole bunch of airspeed for not a whole bunch of power increase. That is your power setting and airspeed for max endurance, okay? So it is important to note that we would be going through this experiment together. How you're going to teach this in the airplane is that, and it's such a great exercise to go through when students are just learning handling and normal cruise attitude by using the horizon and trimming. This is such a great exercise to go through where they can understand the airplane and practice handling at the same time, okay? So how you're going to teach us in the airplane is that first and foremost, the instructor will fly and the student will write down all the numbers. Then after you analyze the data together, then the student flies to try to recreate the same experiment, should come up with roughly the same numbers, okay? So now in the presentation, we're gonna cover pilot decision-making, lookout, and leading the mixture. Decision-making would be, situations where we would need to really pay attention to this. Lookout is important. And at max endurance, at a lowest power setting to keep in the air, you're going to have a nose high attitude. You're not going to be able to see very much. And of course, leading the mixture is important for both of these. Now, summary. In this lesson, we have discussed the drag and power graphs, how to use the POH to find helpful information, and the specific experiment that you do to find flight for maximum range and maximum endurance. This lesson really truly is the first step to understanding the next 4 lessons because it involves the start of use of the power curve and really truly has to be covered before you get into slow flight at all. All right, so then I'm going to stop sharing. That is the presentation. Stop, remind, go through this over and over again. And really, if you're going to create slides or create a presentation very similar to mine, I suggest that you can take all the information, please do, please reiterate it exactly how I've said, make the slides your own, okay? Don't screenshot any of this and just pass it off as your own material, because your student is going to see that and they're going to go, oh, they're just copy and pasting. They don't really know this stuff themselves. If you create a set of slides to look to mirror the information that I've given you in the exact fashion that I've given you, please do it, but make it your own, make it look like your own. Okay. So I hope you guys have a great day and I'll see you soon.